Okay, we will take up today a new topic on permanent magnet machines. In fact, permanent magnet machines are rated to be one of the important energy converters with lot of futuristic scope, okay, both in generating mode as well as an motoring mode. Okay. All this has evolved because of the developments in the following. One is the development of permanent magnets themselves. So, that means the research in material science, the materials which can create high energy density permanent magnets, okay. That is one factor. Second are the new applications which requires use of permanent magnets, and third are the new developments of control possibilities, and it is possible to have converters which can be used along with PM machines for converting the power through power devices and power electronic circuits. Okay. So, all this has developed, and also the developments in DSP, microcontrollers and so on. So, the combination of these developments have made the permanent magnet a very attractive proposition. The fourth is energy efficiency. You may know that renewable energy and energy efficiency are going to be important technologies for the future. Okay. So, everywhere you have to talk of energy efficiency, which would mean any step to improve the efficiency of the equipment that is put in use in all sectors, whether it is domestic sector or industrial sector, etc. And you may know that even a small saving in energy consumed by any device may make a large impact so long as that device is used in millions. For example, that is why people are talking of replacing the bulbs with CFL. Why? Because instead for the same light, it will consume maybe 5 to 10 watts in comparison to 40 or 60 watts in a normal incandescent bulb. Okay. So, you may feel that after all it is only a 10-20 watts saving, but if you consider the millions of devices which are used, it may make a major impact. Similarly, a fan, if it consumes 50 or 60 watts, if you can somehow develop fans which can even make 40 or 45 watt, it will mean 10-15 watt of saving for each fan when in use. Okay. So, that again will be an important development. So, if you can be energy efficient motors which can drive the fan, this is one of the recent emphasis. Similarly, the power consumed by air conditioners. Air conditioners are the major electricity guzzlers in commercial office complexes and so on, and also IT industry. Now, the trend is to use instead of conventional induction motors, if you replace with permanent magnet motors, okay, then what will happen? Because then it will if it can reduce energy consumption or make it more efficient, then it would be a desirable development. So, these are a few of these things, the applications, the possibility controllers, better magnets and better developments have made the permanent magnet machines very useful and attractive. And you may find very varied applications, okay, like generators, they are exploring that it can become a very useful wind electric generator, permanent magnet generator, directly coupled wind electric generator. In fact, I just saw very recent paper which was published in March 2007, okay, March 2007. It says an axial flux permanent magnet synchronous generator for a direct coupled wind turbine system, an axial. So, it is a direct coupled because it's a low speed you will have large number of poles, it will be more like a large disk, and it is perhaps a very useful invention. One can have such PM machines in the picture. Okay. Next, you may find them in automobiles where you have lot of actuators and motor, servo motors, etc. You find them in robotics where lot of movements have to be there, torque producing. So, there you use permanent magnet. Use them in computers because wherever there are small movements, okay, audio equipment, video equipments, okay, CD drives. So, you find them in large numbers, the PM machines, okay, even printers. Okay. So, they are the ones which are hidden actuators, hidden drivers for this. Then it can go to higher capacities for drives, variable frequency drive, variable speed drives, they are thinking of this. Next is electric vehicles, future there will be a lot of electric vehicles. So, the PM machines are considered to compete with other alternative type of motors, right. And satellites which uses basically solar panels. So, there also you may find these devices. Okay. So, we can briefly in the coming few lectures I would like to just discuss and give you a glimpse of the developments of permanent magnet machines. And in a few lectures it is not possible to cover everything because it is a continuously developing type of areas. Okay. Okay, now if you look at the classifications of machines, you see in the PM machines we classify, one is the generator, another is the motor, right. Among the generators the broadly it is the permanent magnet synchronous generators. So, what are the permanent magnets do? They replace the conventional field windings, okay, replace it, and because it make it simple, no windings are there, construction is simple and so on. Only problem is you can't control the flux unlike in the DC or synchronous machines, right. So, that is one with the, if you can put up with those limitations they are attractive. Similarly, on motors you have you can have permanent magnet DC motors or permanent magnet synchronous motors. These are two types of motors, okay. And among the DC motors they are the ones with brushes, they are called brushed DC motors. Brushed means with brushes and commutators. That means you are taking a conventional DC motor and remove the field windings and put the magnets over there, okay. So, that is the brushed DC motor. Other is brushless, that means you do not want to have brushes, okay, and you have the magnet, permanent magnet, okay. Now, you can visualize what will be that type, brushless DC motor, supplies the same DC, but whatever switching, what the commutator does is it switches the windings. So, this switching has to be done electronically, okay, but no brushes must be there, that means no brushes, no commutators, okay. So, you think how can it be achieved, but your supply is DC, but you can have the commutator and brushes removed through a switching, okay. Now, the type are permanent magnet generators, as I told you that low speed which are typically wind energy systems, low speed generators, in fact you can have it in automobiles and several things also. But there is another application which have been considered high speed, maybe 10, 20, 30,000 RPM, even more. These are driven by micro turbines. Micro turbines are typically which are driven by some gas turbines and so on. Nowadays they are talking about this small one. The power in a machine is proportionate to the speed. So, instead of 3000 RPM you can go for 30 or 40,000 rpm, okay, and a high speed ones. What is the problem? I mean, if you have a high speed turbine, you should have no problem, isn't it? Do you anticipate any problem? No, it's mechanically, so long as you have a good bearings which can handle the 30-40,000 rpm, you know, and typically in aircrafts etc., then they are high speed, the turbines are driving, okay. Now what problems that you will face? Huh? No, it is a permanent magnet generator, it is a AC generator. So you have magnets instead of a field winding in the rotor, it is happy, you no slip rings, no brushes, brushless, you just have the rotor, okay. Now this high speed also means high frequency. See, if you have two pole, you know, for a 2 pole 3000 rpm it will give you 50 hertz, same thing at 30,000 will give you 500 hertz or even 3000, 30,500, if it is more it can. So you will have a high frequency, so all you need is you have to convert that into DC and do inversion, okay. High frequency voltages are to be 500 hertz to you make it, they are all power frequency, you must think of a new systems to do. Converter technology has to be appropriately adapted, okay. Okay, then out of the PM motors, permanent magnet motors, I told you one is a brushed with commutator. So what you have is stator is instead of field windings you have magnets only, okay. You fix the magnets and the rotor has the armature, commutator, brushes etc., okay. Is it okay? So there is I hope you have no problem in understanding the construction of this type. Now I come to the brushless permanent magnet DC motors. No brushes should be there, okay. Then but here it is inverted actually. The stator has a polyphase winding and it is fed by a converter. You have a DC, so it has to be fed by a converter, and that means let us say you have the polyphase winding, you have a DC, okay, and rotor is a magnet. Say rotor is a permanent magnet which is rotating, right. Okay. Now when do you pass a current through them? This winding, okay. When will it produce the maximum torque? Is it aligned or it is unaligned? So that means you must again the rotor sensing is important. You must have a rotor position sensing. So if you have, I am just giving you, if you have ABC winding, A winding will be switched to the same voltage source V when it is effectively quadrature to this. So you are doing an electronic commutation, okay, right, and then you know, and same thing will happen, the B winding will switch for the same one at 120 degrees etc., okay. So you need to have a suitable converter which has to do this job. Right. So this is an issue, okay. Let us see what type of converters are used etc. You are aware of 3-phase converters, isn't it, from DC to switch the windings, okay. If you have 3-phase windings you can switch to the DC supply, right, you are aware of that, okay. Then there is another type, this is a side wave, that means you are just having a synchronous motor, right. This is different than a brushless DC. brushless DC is almost, so here your synchronous motor you try to apply a sine wave to the windings, and stator is 3-phase winding fed by the inverter, variable frequency, rotor is the permanent magnet. Okay. So, this you have PMSM, permanent magnet synchronous motor. They are different than permanent magnet brushless DC motor. This one is popularly known as PMBL DC, is not it? So, you must have studied in some other course, I hope, drives or no. Okay. Okay, these are the two different type of technologies. Converters have to be suitably made, okay, on this. Okay. So, as I told you, the emphasis of these machines have increased mainly because of the development in magnets and the material. Okay. Before we actually go into it, I thought I will show you a part of a permanent magnet machine, a small micromotor. These were used in tape recorders, okay, which has been locally made. Okay. I need a volunteer. Can someone come and hold this, please? Okay. Okay. Right. Okay. Just to see. Okay. Right. Okay. Now, this is ultimately the motor. Okay. Now, see its parts are inside are here. So, what I am holding with me are the magnets, okay, and inside is the armature. You see, inside is the armature, and what do you see? You know, it has a how many slots it is having? It has 3 slots and 3 tooth, right. So, there are there are 3 windings which is on each wound on each tooth, okay. All of you see this, right, and which gets into that will become the rotor, and the terminal of that windings will be connected to a commutator and brush. You can imagine how tiny it should be, okay, and this runs, and whenever you apply a DC, then this runs as a motor and drives the tape recorders, okay, or CDs or whatever you say. So, this is the micro motor. So, you have to maintain the speed constant, okay. You have to maintain the speed constant. So, they have a regulator, you know. So, there is a governor. So, these are all parts of what you see here. There is a diode, a resistance, you know, leg and a coil drum. There is a coil drum with, there is a coil, capacitor, there is a IC chip, and there is a PCB, okay, and this is a PCB assembly. So, this whole thing what you see is a control circuit, okay, that will also be fixed to the motor, okay. So, because it has to finally get into an electronic circuit for the drive, okay. Then you have a tag, a brush spring, mechanical tag with brush spring, the damper pad, and tag with sub assembly. There is a bracelet and bearing. You can see the bearing how tiny it is here, okay, right. Then there is this bracket sub assembly, etc. Okay. Now, coming to the motor. So, these are all what you see here are parts which are so tiny, which are external to the machine in some way. Now, this is the stamping. You see the whole thing is, you are seeing the stampings, okay, and from these stampings are assembled together to make the armature. This is the armature, okay, and this is the motor shaft. You can see the motor shaft looks like a rod of an umbrella or something like that, okay, right. It is maybe often it is made from such rods only, okay. Then you see the commutator, this is the commutator washer, okay, this is the commutator segments, the tiny commutator segments, and you have this is the commutator body. So, this you know, each of this commutator body, that means there are it is electrically soldered to the end of 3 windings, okay, they are here. and then what you have, the commutator sub assembly is here, right, which is again fitted to the shaft. This will also go into the shaft. Okay. Then you have the core corner means on you pad up these two sides just to fix up, this is a core corner. Okay. Then this is the core, assembled core here with the shaft and with the commutator assembly, and this is the rotor without timings, etc. That means the wound rotor, you see that each of these each one has two terminals. Okay. They get into the commutator. Okay. And then I think then this is the outer body on which it is placed. For this again this is the this rotor with the commutator. You see the commutator at the top of it. Okay. So this is connected to the commutator. Okay. Right, and I think these are the end plates, etc., and then finally you make the motor. Are you clear? What it, how small, and this way it is called a micromotor, DC micromotor. Okay. I am just this has a brush and commutator. These are magnets, because you see here the magnet is the outer body, okay, which is there, right. I thought this will give you some idea of what is it like to be a permanent magnet motor, which is different than a normal motor. Okay. Okay, we will look at the materials, permanent magnet materials. Okay. Okay, now you may be aware, sorry. Now historic developments of magnet, see each magnet has certain energy. BH is the product of BH, is the energy stored per unit volume in the magnet. Okay. If any one of them is 0, then B is 0 means there is no energy, H is 0. So, BH product is important. So, BH product, maximum BH product, okay, is in 1950 these were it was this much, okay, units, about 5 units or so. Now, if you there were at that time Alnico 5 came, then Alnico 5 and 5.7, that is in 1960, 70 is Alnico 9. These are all the materials which development in 1970. 1980 we had developments in rare earth, samarium, cobalt, etc., where it, you can see from 5 it came almost near 20 here. Okay. Then made a big change in this new material called a neodymium iron boron. This is a new material which is now being very widely used. Which has nearly 40. So, you can see from 5 to 40 means almost 8 times, BA. So, 8 times means your machine size will go down 8 times, because BH product is per unit volume. Okay. So, volume can come down for the same energy handling. So, this is one development which has led to the better development of permanent magnet machines. Okay. Now, if you look at the characteristics, the permanent magnets operate at a certain range of the BH loop. Okay. Now, normal BH, you start with OA, okay, then you go to initial magnetization, is not it? Go to this point OA, is not it? You take a dead magnetic material, you excite it from 0 and go to A, which up to certain H. I mean, of course, here this is plotted as mu naught H, just so that you can have a unit is same. This is B, this is H. Okay. Now, so that is what you will see. So, the starting point is BH loop, hysteresis loop. Okay, you know what is magnetizing force and field intensity. Okay. Then magnetic field intensity, of course, we can, you are aware of this. okay, sorry. So, you say initially B 0 H is 0 and then you start out at the origin and it will follow the curve OA as the external ampere turns are increased. So, you say you take the material, go on, you wind it, put an ampere turns into it and it reaches a point, right. And you are aware that after that you switch off at that point, okay. Switch off at that point. So, it will trace it back, okay. It will trace it back along AB, okay. Let us see where will it trace back, okay. So, let us say it goes trace back through okay AB, right, you have entered here. So, initially it was you have gone here. So, it come to this point, okay. So, now operating point will depend upon the shape of the magnet and the permeance of the surrounding magnetic circuit, okay. So, what the magnet does is if you switch it off, it relaxes along this AB, okay. Now, what point it will operate, what H and B will it give? See, you can place a magnet, okay, as it is, do not connect anything externally, it will just give its own minimum flux, is not it, almost like a, okay, let us see. Now, if a magnet is surrounded by a highly permeable magnetic circuit, highly permeable means make a nice iron piece, okay, almost like a short circuit, like a battery you short it by a wire, it becomes, it draws a very heavy current, you do not short anything at all. So, either have open circuit or a short circuit condition. So, it is called, it is keepered, it is called a, that means you are connecting a magnetic circuit, that means it is keepered, then poles are effectively shorted, so that H becomes 0, that means you almost shorted that, and the flux density is then the value at the point B, that is the remnants of Br, okay. So, if you short that, what we are saying is this will be the point where at this point what H is 0, right. So, this is called the remnants. Sometimes it is also called Br, that is this point, okay. Now, so remnants Br is, remnants is the maximum flux density that can be retained by the magnet at the given temperature after magnetized to saturation, okay. Now, so external amperes turns applied in the opposite direction can cause the magnet's operating point to follow the curve from B through the second quadrant to C. That means, you can apply a negative ampere turns from B, then it will follow up to C as you go on through the negative ampere turn. Let us see what is that route. Okay. So, from these you have taken negative ampere turns and it can go till you apply the negative ampere turns to that point C, right. And I think broadly this is the area of our interest. Okay. Okay. It is magnetized in the opposite direction and the maximum flux density it can retain when keepered is minus Br. So, it can go it has second quadrant to C, again if they are switched off. Now, at C you switch it off, supposing after you apply a minus H you switch it off, then it will relax and along CD, okay, where is that CD? Okay. So, it will follow this path. So, you switch off here and it will follow this path up to D. Okay. And till here you have not applied anything at all. Okay. So, it goes up to minus Br up to that point. That means, when there is a 0 H, there is a minus Br. Okay. So, return the flux density to 0, because there it was minus Br, then you have to again apply some plus H, okay, and that must, so you have to again apply a positive MMF, okay, and then you have a symmetrical hysteresis loop, okay, and you can measure it through a instrument called hysteresis graph. Okay. So, that is, so you are you need to know what is the whole principle involved in this if you want to go to the same curve. So, what you do, from here you apply another MMF. So, it can retrace the path and go here. Okay. So, your main issue of permanent magnet is basically in this region, okay, where it will be providing you a flux, even if you have you want a positive flux, and even if you have a load, because what is minus H means you are applying a load, okay, magnetic load, okay, right, and this point is called the coercivity, okay, that is minus Hc is also. So, you have a remnants here and coercivity here, okay, okay, I will write it again for you. This is this. Okay. So, these are your important points here. Okay. Okay. So, you have this idea called coercivity, which is to bring the flux density to 0 from the original positive remnants. External ampere turns must provide within the magnet a negative magnetizing force, that is minus Hc, called coercivity. Okay. Then of course, from that point you go back and you get the hysteresis loop. Okay. Okay, now if the negative ampere turns are applied starting from point B and switched off at some point R, okay, some other point. Okay, let us see what is that point. Right, I have switch off at some point R here. Okay. I do not go to up to C, switch off at that point, and then what will happen is it will relax in this loop. Okay, this is S, and this has a slope, and this is called the recoil flux density, I mean recoil permeability mu. So, it is a small loop, it relaxes in this. So, it will be in this loop. Okay. So, I am sorry, I have to go back and forth to that figure. Okay. So, you have it is called recoils. It recoils along that line RS. It is a small loop, you can always consider it to be a line, okay, with a slope of mu recoil. Okay. So, the magnet is still keepered means it is shorted. Okay. The operating point ends up at point S. Okay. And if it is shorted, what will happen is it will come to point S, which is less than Br. What is that point S? We can we have to again go back to that curve. Okay. So, this is this point S. So, from R it just traces this small loop. So, it is called a recoil line. So, it depends upon what point you switch, and they may be parallelly doing like that. Okay. So, this is the point it will reach, okay, if you because you remove the, you have switched off already, okay, that is what it will do. So, it traces this line RS and settle on S. So, if the external ampere turns are reapplied in the negative direction between S and R, the operating point returns along SR. Okay. So, these are the certain fundamentals you are expected to know. Okay. See, what we are broadly saying is, suppose you have a magnet with north south. What you normally, if you just keep a magnet, you would have, you have seen, usually flux lines will go like this, isn't it? This you are aware, but they are very very low flux densities. Okay, this is like open circuit. I am not connecting anything to this, but next case is you take the same magnet NS, okay, and then you short it, you have a good iron piece over there. Okay, this iron piece. Then what do you expect? Do you expect the same flux density as here? What do you expect? Supposing here the some point you have a flux density B open circuit, I will say. What will be the flux density here? It will be more than this. So, here in this case B will be approximately equal to Br, because H is almost 0, right, because it is not here, H is almost infinity, isn't it. So, this is like a open circuit, this is like a short circuit, which is often called as keepered. Okay. I hope you understand, this is very critical. Please do not think you have a magnet and keep and do whatever you like, say, okay. Only when you have a magnet, be careful about your watch, that is all, because it is likely to, heavy magnets is likely to distort your watches, right. Now, we have a relative permeability, okay, and so line RS can be taken as a straight line whose slope is equal to the recoil permeability, it is called recoil permeability, mu recoil. Okay. So, the relative permeability is now mu recoil mu naught into H per meter, okay, that will be Henry per meter. Okay. So, mu recoil and mu naught will be the new permeability, it is called relative permeability. Okay. Yeah. Huh? No, it is okay, but we can't close in between. Okay. Now, you have a, okay, you should have sat in this side. Okay. Now, there is a hard permanent magnet material, okay, where hysteresis will be straight line and recoil line is coincide with the second quadrant. Recoil line is with the second quadrant, that is parallel lines, okay, and recoil permeability is usually 1 to 1.1 recoil, say, of this order. Now, these are the materials, ceramic, samarium, cobalt, neodymium, iron, boron. Okay. Of course, there are soft magnetic materials which will have a very low hysteresis loop. Okay. Now, if you look at this is a slope, this is 0.8 here, this is 0.8 here. Okay. This is a hysteresis loop. Now, this can be one recoil line, this is minus mu naught Hc. Okay. And now, what if you make it short circuit, it will operate at this point. If you make it open circuit, it may operate at this point, okay, where B is 0. Now, if you connect some materials in between, it will have any of these points, is not it? Okay. Right. So, this is there is a point which is a BH max. See, BH is should be maximum, okay, product of B and H. Which point you would like to operate? Would you like to operate here, here or here? In between, no, right. So, where it is a BH max here, product BH, this is the BH max curve. So, that is a like a BH max curve is a like a hyperbola, okay, like this, okay, right, and these are for different values of permeability. So, you can connect whatever material you connect, it will operate at, these are the curves, okay, these are called permeance coefficient, okay. So, this is called demagnetization curve, second quadrant, and intersection of the demagnetization curve and the load, this is called a load line. So, what is the operating point will be the load line and the demagnetization curve, okay, that is the operating point. Now, what will be the B it will produce? If you have a circuit, what the B it will produce? If you apply a H over there, it will produce a B, right, and even if you do not apply H, it will produce another component J. So, the first term is the flux density which will produce it if the magnet is not there, and the second one is due to the magnet, isn't it? There are two components, one is due to in any circuit due to its own H, other is due to J, relation between B and H. Okay. So, second term is regarded as a contribution of magnet to flux density within its own volume. If the demagnetization curve is straight, if relative slope and coil permittivity both are unity, then J is constant. So, J is called the magnetization of the magnet, because there is a J which will give you, which is it does not depend upon the point of operation, so long as they are straight lines. So, in most hard magnets the recoil permeability is slightly greater than unity, and there is a slight decrease in J as the negative magnetic force increases. Okay. So, this is reversible down to the knee of the BH loop. Okay. I think these are you can. Okay. Now, the BH max line is a for a given magnet occurs where the demagnetization curve is tangent to the hyperbola of its BH max value. So, the BH max occurs, supposing this is your curve. Now, BH max curve is somewhere. So, this is your, if you put BH max, so that should be that tangent here. Okay. So, this is the operating point. So, you must ideally you must have this as a load curve, load line to operate. Okay, we will skip here. If the coil permeability is unity, these are all not very important statements. We will look at room temperature, neodymium boron has the highest energy product. This is the why we are using neodymium iron boron, it has the highest BH max product. Okay. Now, high remnants and coercivity permit marked reduction in motor frame size for the same output, etc. Okay, let us look at. Actually, these are the BH product of different materials. So, I would only go by the BH max. Alnico is 7.5 and neodymium iron boron is 30. Okay, that is how it is the one, and this is the remnant flux is 1.35 is 1.12 and this coercivity is 0.074 and 1.06 etc. I think other points are relatively less important. Okay. Now, what we will just quickly go through certain science behind it. You have a magnet here and where you are kept with a iron piece with its own length Lk, okay, and this is Lm magnet length and its area. Okay. Now, this is the characteristic BH characteristics, this is the Br. Now, since the permeancy here is small in the sense we have a permeability, it is like a short circuit, okay, and reluctance is small, permeance is high, right. The external reluctance of permeance high means it will have a slope which is nearer to B. So, you will have a high B here, okay, it is a high B point. Now, you can use, there is no, you have not applied any H there. So, the sum of this HM LM plus HK LK is 0, where LM LK is the magnet length and the bar length separately. So, what is the H at the magnet? HM will be minus LK by LM by HK. HK is the H inside the magnet, in the load or the external load. So, the magnet works in the second quadrant with given by this HM. Now, if you place a air gap here, you cut it, then you know here the H is nearly 0, is not it, and with most of the H will be in Lg only. So, it will shift here. So, you will have it will produce a less B, okay. This is the operating point here, you have shifted, okay. So, in this case there is H in the iron is 0 or negligible. So, HM will be minus Lg by Lm into Hg. So, magnet H will be this point, okay, operating HM. Okay. Now, I will take 2-3 minutes now you may consider this to be similar to any electric circuit, like with a battery and an external load. Here the battery is like a magnet and the external load is like the magnetic circuit you will connect to the magnet. Okay. For example, if you connect the magnet in the stator of a machine, what will be the load will be the air gap, the rotor iron and all the things will become a load and will go back in the into the iron. There is also iron parts which are soft magnetic materials which will work as load, and there is this air portion magnet portion is okay. Magnet portion like a source and this like a load. Now, but then you must be careful in handling the magnets. Why I am telling this is in many places people may think it is magnet is nothing great etc. Okay. Now, one thing is you must wear though looks ridiculous, I mean sort of trivial, you must wear safety glasses when handling magnets. People have broken their hands in dealing with magnets, right. And there is an instance where somebody was just holding the magnet, and there was iron piece on the ceiling and it retracted and fell on his head, okay. And several things have happened in places, okay. Now, therefore, it is important when assembling magnets. Say there are two ways. If you want to make permanent magnets, what should you do? You should ask the manufacturers. Bulk of the supplier of neodymium iron boron today, suppliers are in China. China is the one which is producing maximum neodymium iron boron. Okay. So, you can ask them to send you the magnet material and you must have a magnetizer with you, is not it? You must cut it to the proper shape, magnetize it. Otherwise, you ask them to magnetize and send it to you. If they magnetize, send it to you, throughout you must be careful, you are handling a magnetized magnet. Okay. So, it is important. Okay. While assembly, if you have magnetized magnet, you must make sure that it is properly assembled and you must be careful. Okay. When large pole magnet is being assembled from smaller magnets, okay, many times what will happen is you have a you can make a big pole out of small poles also. You can go and put them to small magnets together to make a big magnet. Okay. Then the magnet have a tendency to flip or jump. Okay. So, you work behind a plexiglass screen when experimenting or assembling magnet assemblies. Avoid chipping by impact or hard materials, tools or other magnets. Okay. Then never dry grind rare earth magnets, the powder is combustible, right. Dry grinding is many times you try to grind it, but the magnet material may start burning, okay, because they are combustible. In case of fire, use LP argon or nitrogen dry chemical extinguishers. That is one of the reasons why I say you must read chemistry, okay, because these are all the factors which should combine. Okay, they say that never use water or halogens, etc. Okay. Then PM motors generate voltage when the shaft is rotated. Okay. So, even when disconnected from the supply. So, there will be voltage induced in the windings, okay, in PM machines. So, you may get shock. Okay. So, when assembling a rotor to a stator with either one magnetized, the rotor must be firmly guided and stator firmly located. Never leave magnetized parts open or unprotected. Okay. Though I deliberately included this section in the lecture because magnet safety is very important, unlike the other machines where most of the parts are not live. Okay. So, these are a few precautions you have to take in magnet. So, we have discuss some preliminaries of the magnet materials, etc. In the next lecture, we will discuss about the brushless DC motors. Okay.